Modern-day weather radar consists of a dish that emits extremely short bursts of microwave radiation called pulses, with slightly longer periods in between in which the radar listens for energy returned to the dish. The pulses emanate outward as waves in a narrow beam, and as the beam comes into contact with objects, both meteorological, like rain and hail, and non-meteorological, like birds and leaves, the radiation is scattered in all directions with only a fraction of it bouncing directly back to the dish. The radar observes this backscattered energy during the listening periods in between pulses, and by recording the time it takes the pulse to leave the antenna, strike the target, and return to the antenna, the radar can calculate how far the target is from the dish. The amount of backscattered energy received by the radar is related to the intensity of the targets. Each pulse has a specific phase, which is essentially how far along in its cycle a wave has progressed at a given time. A wave's phase is influenced by its geometry, wavelength, frequency, amplitude, etc. The difference in phase, also called a phase shift, between a transmitted pulse and the energy scattered back to the radar directly correlates to the velocity of the objects, with a greater phase shift representing greater velocity. These phase shifts comprise the Doppler effect, hence why modern weather radars are Doppler radars.
The Chaser Academy is the best deal in storm chasing. Click the join button below this video and find out why.
The number of pulses a radar transmits per second is called the pulse repetition frequency, or PRF. The PRF influences a couple of important quantities called the maximum unambiguous range, or Rmax, and maximum unambiguous velocity, or Vmax. If a radar emits a pulse before the backscattered energy from the previous pulse is received, the radar will be unable to properly determine the range of the target. In other words, the range of the target that the radar measures becomes ambiguous. The maximum unambiguous range is the maximum range from which a transmitted radar pulse can be scattered and received before the next pulse is transmitted. Increasing the PRF decreases the maximum unambiguous range, and vice versa. A radar also has a limit on how much of a phase shift it can detect. If a target is moving so fast that it exceeds the amount of phase shift the radar can detect, its velocity will become ambiguous, meaning that the radar may think that it's stationary or moving the opposite direction at a much different velocity than what it actually is. The maximum unambiguous velocity dictates the maximum range of velocities that can be observed without this ambiguity. We're going to talk more about this later on in this module, but for now, know that as the PRF increases, so does the maximum unambiguous velocity. This creates a dilemma. Increasing the PRF allows us to have a greater breadth of unambiguous velocities, but it would also degrade the maximum unambiguous range, leading to a lot of unreadable data. Decreasing the PRF would give us a much better maximum unambiguous range, but also an increased collection of ambiguous velocities, again leading to erroneous data. Thankfully, radars can operate with an abundance of scanning strategies called volume coverage patterns, or VCPs, to combat this based on the phenomena that are expected within a radar's range. As we know, a radar dish is not stationary, rather it rotates and tilts upward as each full rotation is completed so that we can get a full 360-degree look at what's going on in the lower atmosphere. The full extent, both horizontally and vertically, that a radar scans in one cycle is called a volume. A volume is made up of data at several different elevation angles, also called tilts. When the weather is quiet, the radar can operate in clear air mode, in which it rotates more slowly and scans fewer elevation angles. However, when precipitation is detected, it switches to precipitation mode, which scans more elevation angles more quickly, making it ideal for monitoring rapidly changing severe weather. The wavelength of the pulses a radar emits is also a critical piece of the puzzle. Radars that use shorter wavelength pulses tend to detect smaller particles, meaning higher spatial resolution and more detailed data. However, these particles partially absorb some of this smaller wavelength radiation, a process called attenuation, which leads to degraded data quality the more particles the beam encounters as it goes outward from the dish. Radars are divided into several different bands based on their pulse wavelength. WSR-88Ds, which are National Weather Service radars here in the US, operate at S-band with a wavelength of 8 to 15 centimeters. This is relatively large, making it a good choice for both close-range and distant weather observation without significant impacts from attenuation. Terminal Doppler weather radars, or TDWRs, which are found at airports, are C-band radars which use a 4 to 8 centimeter wavelength. This increases spatial resolution but also makes them more susceptible to attenuation, As a result, they are better suited for short-range weather observation. Many mobile radars, like Doppler on wheels, operate with even smaller wavelengths at X-band, which yields extremely high-resolution, close-range data, but frequent issues with attenuation. Alright, now that we've introduced some of the basics of weather radar, let's dive into an overview of the data that radars output. Perhaps the most widely recognized radar product is reflectivity, which is the amount of energy that returns to the radar after scattering back from a target. Reflectivity tells us where precipitation is occurring and how intense that precipitation is, and it's measured in decibels, or dBz, where z is the meteorological variable for reflectivity. In general, the higher the reflectivity, the heavier the precipitation. Reflectivity values below 40 dBz typically indicate light precipitation, while values above 60 to 65 dBz generally represent extremely heavy precipitation, sometimes including hail. These guidelines can vary based on the size of the raindrops. Small drop sizes, like those in tropical systems, return less energy to the radar and, therefore, yield lower reflectivity values than the larger drops of a typical thunderstorm, despite equally torrential rainfall. As we discussed earlier, Doppler radars also measure the phase shift between an emitted pulse and the energy scattered back to the radar to estimate velocity. A target's velocity is comprised of the speed and direction of the target. Negative velocities, which are illustrated as greens, blues, and pinks on typical radar programs, represent targets that are moving toward the radar. These are also called inbound velocities. On the other hand, positive velocities, your reds, oranges, and browns, represent targets that are moving away from the radar. These are outbound velocities. Velocities near zero show up as gray. Depending on the radar program you're using, velocity is measured in either knots or miles per hour. Typically, higher velocity values indicate targets moving more quickly, but, as we mentioned earlier, this depends on the radar's maximum unambiguous velocity. Again, we'll get into this in depth later on in this module. The velocity of a target that you see on a radar program will almost always be slightly less than the actual velocity of the target because radars are at fixed locations, meaning that they can only measure how fast a target is moving toward or away from the radar itself. This is called radial velocity. Every azimuth angle, which is the radar beam's angle from due north, is associated with a radial. Radial velocity is equal to the actual velocity of the target only when the target's motion is directly toward or away from the radar. In other words, directly along a radial. Therefore, the greater the angle between the radar beam and the target's motion, the less the portion of the target's actual velocity that will be sampled, and the less the radial velocity will be. If a target is moving perfectly perpendicular to the radar beam, its radial velocity will be zero. In addition, standard radial velocity, which I'll refer to as just velocity or base velocity from here on out, is the target's velocity relative to the ground. However, storms and their small-scale phenomena, like tornadoes, move with respect to the ground, which can make it difficult to obtain proper velocity measurements. For example, if a storm has 40 mile per hour winds and is moving directly at the radar at 30 miles per hour, the radar will output an erroneous base velocity of 70 miles per hour. To combat this, we can use a product called storm relative velocity, which subtracts out the storm motion. This can make it much easier to discern areas of rotation within the broader wind field. Reflectivity and velocity are the two foundational products of weather radar and can tell us a number of things about a storm's behavior and characteristics. However, they only give us a two-dimensional look at targets. Before the early 2010s, WSR-88D radars could only produce reflectivity and velocity measurements, but starting in 2012, the entire network was upgraded to have dual polarization capabilities. Let me explain. The pulses of energy emitted by a radar oscillate in a specific plane, much like the ripples in a calm pond after you toss a pebble into the water. The orientation of the waves is a property called polarization. Prior to the upgrade, radars could only send out pulses that were oriented horizontally, in other words, horizontally polarized. Today, WSR-88D radars send out pulses that are polarized in both the horizontal and vertical, which allows us to obtain vital information about the size, shape, and orientation of targets rather than just their intensity and velocity. Dual polarization yields a few additional products that can be extremely helpful, especially in severe weather situations. The first is called correlation coefficient, shortened to CC or ρHV. Correlation coefficient compares the consistency between backscattered power in the horizontal and vertical planes. In simple terms, it tells us how similar or correlated the targets are that the radar samples. Correlation coefficient is unitless and ranges from 0 to 1. If targets have similar shapes and sizes, the correlation coefficient will be close to 1, but if their shapes and sizes are quite varied, correlation coefficient will decrease. For example, if a storm or a portion of a storm consists of only raindrops, the associated correlation coefficient will be near 1, as all the targets are quite similar to one another. However, if a storm consists of a mix of raindrops and large hail, the correlation coefficient may decrease given reduced consistency among the targets. Correlation coefficient is also a good discriminator between meteorological and non-meteorological targets, with most non-meteorological targets registering a CC value below 0.9. The exception is large wet hail and large wet snowflakes, which typically yield CC values between 0.8 and 0.97. The next dual polarization product of note is differential reflectivity, or ZDR, which is essentially the ratio of the backscattered energy in the horizontal plane to the backscattered energy in the vertical plane. After a bit of mathematical cleanup, we get a range of possible ZDR values between positive and negative 7.9 decibels. Differential reflectivity gives us valuable insight into the orientation of targets being sampled. ZDR values near 0 mean that the backscattered energy was similar between the horizontal and vertical planes, indicating more spherical targets like small raindrops or hail. Highly positive ZDR values suggest that targets are much wider than they are tall, such as large raindrops that flatten out as they fall. The opposite is true for highly negative ZDR values. They indicate targets that are much taller than they are wide, such as falling ice crystals or elongated snowflakes. Highly negative ZDR values are quite rare in severe weather situations. The final dual polarization product we'll discuss is specific differential phase, or KDP. KDP is derived from a similar product called differential phase shift, or FDP. In essence, FDP is a measure of attenuation in the horizontal and vertical planes. It can be a bit cumbersome to analyze, so KDP is much more commonly used instead. KDP shows the gradient of FDP. In other words, how phase shift, and in turn attenuation, changes in the horizontal and vertical over a given distance along a radial. Since phase shift is measured in degrees, KDP has units of degrees per kilometer and ranges from -2 to 10. Increasing values of KDP represent an increase in the size and concentration of raindrops, which can attenuate the radar beam more. This suggests heavier rainfall. KDP may vary between areas of precipitation, even if reflectivity among these areas is similar. We'll first hone in on the time leading up to convective initiation. This is a time in which you'll mostly be looking at those other tools in your toolkit, along with using your eyes, but radar does come in handy before storms fire, particularly in the identification of boundaries. Boundaries denote the interface between cooler, more stable air and warmer, more unstable air, and often show up on radar reflectivity as fine lines, even though the boundaries themselves don't produce precipitation. This is a product of the fact that winds generally come together or converge along boundaries. As winds converge along a boundary, so do particulates, dust, water droplets, bugs, etc. These conglomerate, and the radar beam detects this increased concentration of particles, forming a fine line that demarcates the boundary's location. As you may know, surface boundaries often become a focus for convective initiation, and tornado chances can increase in supercells that track along boundaries, so identifying them is a critical part of the forecasting and nowcasting process. Surface observations and satellite imagery may often be more reliable tools to use to locate boundaries, but radar can still be helpful as well, especially in diagnosing the motion and intricate structure of the boundaries themselves. When you're forecasting or selecting a target for a particular chase day, it's good practice to take a look at the radar going back to the evening prior to the event in question. This can help you identify any potential boundary-producing convective complexes that may have traversed the area of interest in the lead-up to your chase. These complexes can emit ample rain-cooled air, or outflow, which often leaves behind an outflow boundary or boundaries in its wake. To do this, a radar mosaic, such as the one from the College of DuPage website, can be helpful, as it gives a broad-scale view of the data from all the radars in an area, not just one radar, in a single image or loop. In this example from May 24, 2008, an expansive convective complex developed on the evening of the 23rd and persisted through the morning of the 24th. Behind it, we would expect to see a mass of rain-cooled air, whose southern extent would be demarcated by an outflow boundary trailing from the complex's southern flank. The outflow boundary itself was somewhat unclear on mosaic radar, but surface observations confirmed its existence, and sure enough, a tornadic supercell developed along it that afternoon. While many outflow boundaries do favor increased tornado potential in storms that track along them, this is not always the case. The boundary must be oriented relatively parallel to storm motion so that storms can anchor to and track along it. Otherwise, storms may quickly cross the boundary into cooler, more stable air, which is unfavorable for tornadoes. The movement of the outflow boundary must be assessed as well. Slow-moving or stationary boundaries are most favorable for tornadic supercells, as they give storms a better chance to track along them without getting undercut by cool, stable air. Boundaries that move quickly or surge are still able to initiate storms, but they quickly move to the cool side of the boundary, becoming elevated above the cooler, more stable air, and losing access to warm, moist inflow that exists on the warm side of the boundary. Elevated storms have very low tornado potential because of this, while storms that track along or on the warm side of a boundary are typically surface-based, meaning that they're able to draw in inflow rooted at the surface that's warm, moist, and unstable, which aids in tornado production. Sometimes these rules can be ignored if the boundary is diffuse, in other words, when the change in temperature is more subtle across the boundary. In these situations, the air on the cool side of the boundary may not be stable enough to inhibit surface-based storm development, and generally more backed surface winds on the cool side of the boundary, i.e. more southeasterly or easterly winds, can increase low-level shear to aid in supercell tornado genesis, even though the storms are technically displaced to the cool side of the boundary. This happens somewhat frequently in higher terrain areas like Colorado or the Caprock of West Texas. A look at surface observations can provide confirmation of how strong the temperature gradient is across a boundary. Another type of boundary that's similar to an outflow boundary is a sea or lake breeze boundary. These exist in coastal regions like Florida and in areas near the shores of large lakes, such as in the Great Lakes region. On sunny days, the ground heats up more quickly than the water, which induces a circulation that draws cooler air inland from over the water source. The interface between the warmer inland air mass and the cooler air mass moving ashore creates a boundary, and it can often help initiate thunderstorms in the same way that outflow boundaries do. Terrain-induced convergence boundaries can also show up well on radar. These develop when topographical features manipulate airflow around them such that low-level winds converge, and they can provide the impetus for storm development. These boundaries are typically stationary, but because they are simply wind shift boundaries and do not involve temperature gradients, it doesn't matter which side of the boundary storms develop on or migrate into in terms of whether they are elevated or surface-based. As we mentioned previously, along the boundary itself and the side of the boundary that has more backed low-level winds tends to be most favorable for tornadic supercells as long as the other ingredients are in place. In this example, the fine line on reflectivity you see here denotes northern Arizona's Mogollon Rim Convergence Zone, or MRCZ. Within the Little Colorado River Valley, winds typically flow from southeast to northwest overnight through the morning and early afternoon. When the background flow takes on a westerly component, winds converge within the river valley, and the development of the MRCZ occurs. The Denver Convergence Vorticity Zone, or DCVZ, in northeast Colorado is another notable one. The DCVZ occurs when low-level southeasterly winds flow up and over the Palmer Divide, an east-west protrusion of higher terrain just south of Denver. Due to friction, these winds bend toward the northwest and can collide with northwesterly winds flowing down the slopes of the Rockies, creating a convergence zone that's typically situated just east or southeast of Denver. In this example, note the stationary fine line in reflectivity that was draped through the eastern portions of the metro, evidence of a DCVZ boundary in place. When analyzing these terrain-induced convergence zones, you can also use the velocity product to identify areas of vorticity or spin along the boundary, which can be stretched into the vertical to aid in non-supercell landspout tornado genesis underneath nascent updrafts. Fronts and dry lines can also be identified using radar, and the reflectivity fine lines associated with these features can often be quite sharp, like this dry line in southwest Kansas. As you may know, the dry line is a boundary between hot, dry air to the west and warm, moist air to the east that can initiate storms in many severe weather environments. Prior knowledge of the environment is necessary to correctly identify which type of boundary the radar is depicting. In addition to identifying boundaries, radar can also help you see areas of circulation. These circulations can be convection-induced or terrain-induced. One of the best examples of the latter is the Denver Cyclone. The Denver cyclone is not the same thing as the DCVZ, which we mentioned earlier, but both have to do with the terrain features present in northeast Colorado. The Denver cyclone is a cyclonic or counterclockwise circulation that develops within the lower elevations in and around the Denver metro area as low-level southeasterly flow goes up and over the Palmer Divide. The flow is both bent by friction toward the northwest as it goes over the Palmer Divide and blocked by the massive obstruction that is the Rocky Mountains, so it curves back to the south and creates a cyclonic circulation. A DCVZ boundary often does develop when the Denver cyclone is in place, but it can occur without the assistance from the cyclone as well. Here's an example of the Denver cyclone in action. Notice the broad counterclockwise flow in the weak reflectivity echoes near Denver. These kinds of circulations can produce enhanced lift that promotes thunderstorm development and provide additional low-level vorticity or spin along with the enhanced low-level wind shear, especially where winds are most backed, that can favor tornadic activity of both the non-supercell and supercell variety. Radar can also highlight circulations in the form of horizontal convective rolls. Called HCRs for short, horizontal convective rolls are adjacent vortices that rotate opposite one another, exist in groups, and are oriented horizontally, generally parallel to the average wind in the low levels of the atmosphere. Within the region where HCRs are present, long streets of cumulus clouds develop within the rising branch of the circulations, i.e., where wind converges between adjacent convective rolls. HCRs are commonly found in the warm sector prior to and sometimes during convective development and are often a sign of lingering low-level stability. Once this stability erodes, so will the HCRs, and storms can initiate and become surface-based. If storms move into an area where HCRs remain stubborn, they may remain somewhat elevated. In this example, widespread horizontal convective rolls were in place across southwest Oklahoma and northwest Texas leading up to and during convective initiation, but notice how they erode with northern extent as storms mature. The storms move into the HCR-free area of southwest Oklahoma and become quite robust, going on to produce a significant tornado later on in the day. Sometimes HCRs can actually initiate storms themselves, especially when they intersect a boundary such as a dryline or outflow boundary. Alright, now that we've talked about how to use radar during the pre-convective stage, let's move on to convective initiation. Knowing where storms are initiating is critical in how you adjust your target and navigational strategies on a chase day. Again, other tools can help with this, such as satellite and visual reconnaissance, but often radar can provide the first clue that storms are initiating. The easiest thing to look for is what we call blips on reflectivity. These are small spots of slightly enhanced reflectivity that appear seemingly out of nowhere and are the first sign that nascent updrafts are producing precipitation. Blips will often go on to become robust storms, but in certain situations they may fail to intensify and even fizzle out before new blips take off. This means that either the cap is still a bit too strong to support updraft maturation, choking off the young storms before they can intensify, or the background forcing is still too weak. In other words, the atmosphere has destabilized enough to support storm initiation, but large-scale forcing for ascent is too weak to support the maintenance of those storms. A working knowledge of how the environment is evolving is key to understanding why storm maturation attempts are failing. One radar product that's useful in monitoring updraft intensity during and after initiation is the EchoTops product, which shows the maximum height of precipitation echoes detected by the radar that exceed 18 dBz between 5,000 and 70,000 feet above radar level.
The Chaser Academy is the best deal in storm chasing, and it costs less than a combo meal at McDonald's. Unlock instant access to exclusive storm chasing presentations, participate in live group coaching sessions, and get answers to all of your questions in the unlimited Q&A chat. Whether you're a beginner, a veteran, or somewhere in between, our expert coaches will help you take your storm chasing experience to the next level. Click the join button below this video or on our profile page and enroll in the Chaser Academy right now.
A sister product to EchoTops is Enhanced EchoTops, which helps smooth out irregularities that can sometimes appear in EchoTops output and identifies areas where the radar could not compute a cloud top height. However, the crux of what each product represents is the same. In essence, they estimate the height corresponding to the top of an area of precipitation, and they can be a decent proxy for how tall developing or ongoing thunderstorms are. For example, the value at the center of the bullseye in this enhanced EchoTops image is 62,000 feet, which means that the radar found the highest level at which there were precipitation echoes greater than 18 dBz to be 62,000 feet above radar level. The greater the echo top's value is at a given point, the taller and stronger the updraft or storm is. Prior to the point at which precipitation reaches the surface, echo tops can help you identify which updrafts are strongest and may turn into bona fide storms. In a typical severe weather setup, you may see echo tops readings of 30 to 40,000 plus feet before precipitation occurs at the surface with a given storm, so this can be a good sign that storms are initiating. Of course, storm height depends on the vertical configuration of the instability profile, so this is not always the case, but in a good chunk of severe weather setups, this works fairly well. After initiation, the echo tops product can tell you which storms in a batch of young storms are the most robust and may hold the greatest severe weather potential in the near term. Now, just one note about the echo tops products. Never use echo tops to analyze updrafts that are close to the radar site you're using. In these scenarios, the highest elevation angle that the radar is scanning may not come close to the actual top of the region of precipitation, which yields vastly underestimated or missing echo tops data. Instead, select a radar that can still effectively sample the storms but is farther away. For example, even though these storms are near the Oklahoma City radar site, you'd want to use a site like Tulsa or Frederick to properly analyze echo tops. Once storms initiate, radar can illuminate several signs of storm intensification. In a general sense, strengthening reflectivity and the development of tight reflectivity gradients signify that a storm is intensifying. Essentially, the storm transforms from somewhat of an amorphous blob to a much more shapely state with a tight reflectivity gradient as you go in toward the center of the storm. In addition, the upward advance of strong reflectivities to higher and higher elevation angles also suggests that a storm is strengthening. Another sign of an intensifying updraft is the development of a bounded weak echo region, or BWER, which is a small region of lower reflectivities surrounded by higher reflectivities in the mid-levels of a storm. A BWER occurs when an updraft is so intense that it displaces developing precipitation particles to much higher levels within a storm, leaving a relative void in reflectivities. It's a sign that an updraft is quite strong and often indicates that a storm is becoming or has become severe. We can also continue to monitor the echo tops or enhanced echo tops product to identify which developing storm or storms may have the highest severe weather potential. This can be a bit tricky as updrafts often fluctuate in intensity during the maturation process, leading to oscillating echo tops readings. However, storms that are fairly consistently exhibiting the highest echo tops may have the highest potential for severe hazards. Finally, something to watch for closely is splitting storms. This is simply when an individual storm splits into two distinct storms. The original storm, which is your right mover or right split, as it tends to move to the right of the mean flow, and a left mover or left split, which moves to the left of the mean flow. In supercell environments, left movers take on anticyclonic or clockwise rotation and tend to produce mostly large hail, while right movers rotate cyclonically or counterclockwise and can produce all severe hazards, including tornadoes. Storm splits often occur in the early portion of the convective life cycle thanks to the physics and dynamics intrinsic to supercells. Oftentimes, left splits will die off while right splits intensify. However, in certain environments, left splits are favored and can become robust, even more so than right splits. A telltale sign of a splitting storm is when a storm takes on the appearance of having two distinct reflectivity cores. In this example, note how reflectivity is enhanced on the northern flank of the ongoing storm alongside the enhanced reflectivity within the ongoing storm itself. We then see a clean break, with the left split moving off to the northeast and the right split intensifying and moving off to the southeast. This can also be confirmed visually via two separate precipitation shafts. Keep an eye out for splitting storms, as left splits can sometimes produce even larger hail than right splits, and left splits from separate areas of convection can interact or merge with mature storms, which can induce drastic changes in the mature storm's behavior, from complete dissipation to tornado genesis. We're going to continue our journey into the convective life cycle by focusing on supercells. These are the storms that are sought after by most storm chasers, so we're going to show you how to use radar to identify important supercell features and characteristics, along with some signatures that are linked to certain supercell behaviors. We'll also briefly discuss convective systems and the various ways in which they can appear on radar. So without further ado, let's go ahead and get started. As a quick refresher, supercells are thunderstorms that spin. They're comprised of a rotating updraft called a mesocyclone, and the storm scale dynamics at work within supercells help them persist for long periods of time. In most cases, supercells are favored in unstable environments with ample deep layer wind shear. more specifically when winds increase in speed and veer, or turn in a clockwise fashion, with height. This displaces a storm's rain-cooled downdraft from its updraft, aiding in the storm's longevity, and it creates horizontally oriented tubes of spinning air that are tilted, stretched, and ingested by updrafts, which allows the entire updraft to rotate. Supercells can produce all severe hazards, including damaging winds, hail, and tornadoes, and the vast majority of strong to violent tornadoes come from supercells. The first sign that a storm is transitioning into a supercell is a distinct change in its presentation in radar reflectivity. The storm tends to take on a slightly more triangular shape, pointing back into the mid-level winds, and often it becomes more concave, attaining somewhat of a kidney bean appearance indicative of strengthening rotation and inflow into the storm. As we discussed in the previous episode, intensifying storms frequently feature tight reflectivity gradients around their edges. This is particularly true on the inflow side of a supercell. Here, the gradient demarcates the interface between warm, moist inflow and rain-cooled outflow from the storm's precipitation core. In addition, developing supercells often exhibit something called a V-notch on their downstream side relative to the mid-level winds. Also called a flying eagle shape, it happens as flow is diverted around the core of the intense updraft, which acts as a barrier. A supercell's mesocyclone is also identifiable in velocity data. As a storm transitions into a supercell, it will first display rotation at higher elevation angles, i.e. in the storm's mid-levels. In simple terms, rotation is evident on radar when an area of enhanced inbound velocities is immediately adjacent to an area of enhanced outbound velocities straddling a radial. Again, this first happens aloft, which is indicative of a strengthening mid-level mesocyclone, and then at lower elevation angles. The development of a low-level mesocyclone can be a precursor to tornado genesis if the environment is favorable. Sometimes the reflectivity structure of a storm may lend ambiguity to whether or not it's a supercell, but looking for a low and mid-level mesocyclone can help clear things up. As a supercell matures, it often develops an appendage on its southwest flank, northwest in the southern hemisphere, called a hook echo. The development of a hook echo represents precipitation wrapping around the storm's mesocyclone. A hook echo's presence only signifies a strong mesocyclone and does not confirm that a tornado is in progress, but tornadic activity does tend to occur at the tip of the hook. The generally precipitation-free region feeding into a supercell between its main area of precipitation and its hook echo is called the inflow notch, which is where warm, moist inflow winds rush into the mesocyclone. From a supercell's radar presentation, we can identify the locations of several important storm components. The actual updraft of a supercell lies in the storm's inflow region between its forward flank and its rear flank. With respect to winds aloft, a supercell's forward flank is always ahead of the updraft, as the mid and upper level environmental flow pushes the bulk of the storm's precipitation downwind, and its rear flank is positioned on the backside of the updraft. Within the forward flank of a supercell exists the precipitation core, which is comprised of heavy rain and hail. The core is frequently represented by a region of enhanced reflectivity, often above 60 dBz. Associated with the core is the forward flank downdraft, or FFD, which consists of the outflow winds caused by the storm's rain-cooled downdraft as it hits the ground and spreads out. While the outflow boundary from the forward flank downdraft, or the forward flank downdraft gust front, is not always visible on radar, it can often be confirmed visually by the development of a shelf cloud at the leading edge of a supercell's core. Moving to the backside of the storm, we find the rear flank downdraft, or RFD. The RFD is a current of relatively warm, dry, mid-level air that is forced downward on the backside of a supercell. A supercell's updraft acts as a barrier to airflow. Air can't go through the storm, so some of it gets forced downward and wraps around the mesocyclone. This is the RFD, and it too spreads out as it hits the ground, forming a rear flank downdraft gust front. Sometimes the RFD gust front is visible on radar as a reflectivity fine line emanating from the tip of the hook echo. RFD is critical in tornado production in supercells, and tornadoes tend to form at the interface between the forward flank and rear flank downdraft gust fronts and the storm's inflow. Supercells require a delicate balance of inflow and outflow to become tornadic. If a supercell's forward flank or rear flank downdraft is too strong or too cool, the resultant outflow can undercut the storm, deeming it outflow dominant, which is unfavorable for tornado production. On radar, a storm's transition to outflow dominance is evident when either the forward flank or rear flank downdraft gust front surges out ahead of and detaches from the storm. Excessively strong RFD can deform a supercell's hook echo into more of a dogleg, bowing outward instead of curving inward. This is a classic sign of outflow dominance. However, storms can recover, so just because a storm is outflow dominant does not mean it will stay that way for the remainder of its life. Supercells are categorized by how much precipitation they produce and how that precipitation is organized within the storm. Low precipitation, or LP supercells, are typically quite small and exhibit an overall lack of precipitation and/or precipitation that is shunted well away from the mesocyclone region of the storm. LP supercells tend to look fairly benign on radar, with limited reflectivity values given the overall lack of precipitation. Oftentimes, they do not yield much of a hook echo, if any at all. Classic supercells are those you'll often see in textbooks. They tend to have a flat, rain-free updraft base adjacent to the precipitation core, which has been shunted downstream. The radar presentation of a classic supercell typically consists of many of the features we've discussed previously, most notably including a well-defined hook echo. High precipitation, or HP supercells, produce a lot of precipitation, much of which is co-located with the mesocyclone, causing important storm features, including tornadoes, to become rain-wrapped and difficult to see. Instead of being vented away from the mesocyclone region of the storm, precipitation is often vented ahead of and around an HP supercell's mesocyclone region. HP supercells often maintain a kidney bean-like appearance on radar as precipitation fills the inflow notch and the hook echo becomes less clear. In addition, a special type of supercell called a mini supercell, named for its small size, can also be identified on radar. Mini supercells occur in environments with weaker storm relative inflow, which corresponds to less mass ingested by a supercell and, in turn, a smaller storm. While mini supercells can exhibit hook echoes on radar, they tend to feature a kidney bean shape like HP supercells, although mini supercells by nature produce less precipitation. And of course, their reflectivity footprint will be quite a bit smaller than a normal supercell's. Alright, let's briefly switch gears from supercells to convective systems. Unlike a supercell, which tends to be more isolated, a convective system consists of a number of storms in close proximity to one another, often organized in a linear fashion. The technical term for these kinds of systems is mesoscale convective system, or MCS for short. The most prototypical type of MCS is the quasi-linear convective system, or QLCS, more commonly known as a squall line. A QLCS features a group of storms organized in a relatively spatially continuous line and thus will appear on radar reflectivity as a long line of high dBz values. As outlined in Parker and Johnson 2000, there are three main types of QLCSs, each favored in different environmental conditions. The first of these is called a trailing stratiform system. In this case, a large area of stratiform rain, or rain that is not caused by convective thunderstorms, exists behind the main line of storms. Trailing stratiform systems tend to move fairly quickly. Next is a leading stratiform system in which the aforementioned area of stratiform rain is situated ahead of the main band of storms. These often move more slowly than trailing stratiform systems. Finally, a parallel stratiform system is a QLCS in which the area of stratiform rain is located parallel to and to the left of the main band of storms, relative to the QLCS's motion. While they're often somewhat symmetrical, QLCSs can also feature irregularities and asymmetries that signify localized differences in intensity and potential severe hazards. Individual supercells will sometimes become embedded within the broader line of storms. In these cases, you'll be able to pick out the classic supercell shape, sometimes including the hook echo, within the line on reflectivity. Another way a QLCS can be deformed is when strong downdraft winds force part of or even the entire line to bow outward, which is called a bow echo. We'll discuss bow echoes and the mechanisms behind them later on in this module. When a squall line features multiple bow echoes or even multiple embedded supercells along its length, it can deform into a more wave-like configuration called a line echo wave pattern, or loop. Intense damaging winds and tornadoes are favored severe hazards at and near the bulges in the line. Large hail signatures are much less complex than tornado vortex signatures, but they can be equally important to look for when storm chasing. One of the most basic signs that hail may be occurring within a storm is an increase in reflectivity. This can happen both at the lowest elevation angle and aloft. In fact, increasing reflectivities above about 10 to 20,000 feet off the ground is a reliable signal of large hail production. Typically, large hail is associated with reflectivity values in excess of about 55 dBz. However, just because reflectivity exceeds this threshold within an area of precipitation does not mean that hail is actually falling, as heavy rain can yield similarly enhanced reflectivities. This is where dual polarization products come in. Because radars with dual polarization capabilities can decipher the horizontal and vertical characteristics of targets, they can often differentiate between rain and hail. Differential reflectivity is quite effective in analyzing storms for large hail. Because large hailstones tend to be somewhat spherical and tumble as they fall, ZDR often decreases to near zero in areas where large hail is present. Although not as reliable as ZDR, correlation coefficient can also be used to identify areas of large hail. In a volume that contains a mix of rain and hail, or one that consists of giant hailstones with irregular shapes and sizes, the similarity in the characteristics of targets decreases relative to that of a volume of all rain, which yields decreased correlation coefficient values generally below 0.95. These products should be used in tandem with base reflectivity. Areas of depressed differential reflectivity and correlation coefficient associated with hail will always be coincident with intense reflectivities. In supercells, large hail is most often found just downstream of the mesocyclone and hook echo if one is present. Small hailstones, generally less than 1.5 to 2 centimeters in diameter, are often coated in lots of water and therefore return increased power back to the radar. Thus, they often appear similar to giant raindrops on radar with high reflectivity and ZDR, so if you see significantly enhanced reflectivities within a storm, say above 70 dBz, it often represents large amounts of small hail rather than large to giant hail. However, large to giant hail can sometimes be associated with these significantly enhanced reflectivities, and dual polarization products can help us determine whether or not this is the case, as discussed earlier. One signature in particular that's an extremely reliable indicator of large hail is a three-body scatter spike, or TBSS. A three-body scatter spike, also called a hail spike, appears as a spike of slightly enhanced reflectivity that protrudes out the side of the storm opposite the radar. A TBSS is not comprised of precipitation or actual meteorological targets. Instead, it's an artifact that sometimes occurs as the radar beam interacts with large wet hail. As energy within the radar beam hits large wet hail within a storm, some of it gets reflected toward the ground, then back to the storm, then back toward the radar. It's scattered 3 times, hence the name three-body scatter spike. This portion of the energy returns to the radar slightly after the remainder of the energy returns, so the radar thinks that these echoes are slightly farther along the radial than they actually are, creating the spike on the side of the storm opposite the radar. A TBSS will also show up in other radar products, including velocity and the suite of dual polarization products. Notice the significantly decreased correlation coefficient within the TBSS, indicative of non-meteorological returns. We're going to move on to damaging straight-line winds. They may not get as much notoriety as tornadoes, but they can be equally as impactful, so it's important to know how to analyze radar data for strong straight-line winds. The velocity of a target that's displayed on a radar program will almost always be slightly less than the actual velocity of the target. This is because radars are at fixed locations, meaning that they can only measure how fast a target is moving toward or away from the radar itself, i.e. along a radial, hence why it's called radial velocity. Therefore, when you're analyzing velocity data for potentially damaging winds, the radar may slightly underestimate the actual winds within a storm or storm complex. On the flip side, the velocities that you see at the lowest elevation angle are almost always stronger than what actually reaches and spreads out along the surface. Remember that the radar beam gets farther and farther from the surface the more it extends outward from the radar site, so even if you're analyzing data at the lowest elevation angle, you're still getting a look at the storm that's quite a ways from the surface, especially if the storm is somewhat distant to the radar site. Also, friction from topography and land cover that occurs at and near the surface can cause winds to decelerate. Finally, remember that the greater the angle between the radar beam and the target's motion, the less the portion of the target's actual velocity that will be sampled, and the less the radial velocity will be. If a target is moving perfectly perpendicular to the radar beam, its radial velocity will be 0. So, if you're analyzing an intense storm complex that you think might be producing damaging straight-line winds, but don't see any evidence of damaging straight-line winds on radar, check to see if the winds are blowing more perpendicular to the radar beam. With these notes in mind, let's get into some signatures that can accompany damaging winds on radar. The first of these is a downburst signature. As the strong winds within a downburst reach the surface, they spread out both toward and away from the radar. Therefore, downbursts are accompanied by localized divergence signatures in velocity data, within which an area of enhanced outbound velocities lies adjacent to and on the far side relative to the radar of an area of enhanced inbound velocities. The areas of enhanced inbounds and outbounds tend to spread apart from one another and weaken with time. Base velocity should be used to interpret downburst signatures, unlike rotational signatures, which are best analyzed via storm relative velocity. At the center of the downburst, enhanced reflectivity values and an increase in KDP may appear as well. These are associated with the cascade of heavy precipitation that often accompanies a downburst. Downburst production within a storm is a sign that that storm may be outflow dominant, which is unfavorable for tornadoes. Damaging winds are often the main hazard in linear convective systems, and there are a number of signatures that can help indicate whether or not a QLCS is producing them. Strong downdraft winds can force part of or even the entirety of a squall line to bow outward, which is called a bow echo. Portions of QLCSs that bow outward are often associated with more intense surface winds than other areas of the line. Bow echoes tend to feature a very strong, tight reflectivity gradient on their leading edge. In addition, significant damaging winds are more likely if the gust front or outflow boundary associated with the QLCS or specific bow echo remains close to the leading edge of the complex. An outflow boundary that surges well ahead of a QLCS or bow echo, as in the southern portion of this QLCS here, is not as favorable for significant damaging winds, as it tends to diminish updrafts within the line and decrease the overall intensity of the complex. A common feature of bow echoes is a rear inflow jet, which is a current of fast-moving air that feeds into the backside of a QLCS, originating aloft and often descending down to the surface, causing the complex to bow outward. The most intense surface winds often occur along the rear inflow jet at the apex of the bow. Because the rear inflow jet is often cooler and drier than the surrounding air, it can enhance downdraft strength within the QLCS via evaporative cooling, leading to more intense surface winds, and it can also allow the QLCS to accelerate and persist for a longer duration. On radar, the rear inflow jet is manifested as an area of enhanced velocities on the backside of an ongoing bow echo, both at the lowest elevation angle and aloft. Sometimes rear inflow notches develop, which are small channels of weak reflectivity in the lowest 1 to 2 kilometers above radar level that signal the arrival of the rear inflow jet at the surface and represent localized enhancements of the winds within the rear inflow jet. Tornadic circulations often occur just north of the apex of the bow. Before we get into the nitty-gritty of tornadic radar signatures, let's first discuss how to properly identify horizontal wind shear using velocity data. In most cases, shear signatures, especially those that are important in storm chasing, come in the form of couplets, which are highly localized features in which an area of enhanced inbound velocities is immediately adjacent to an area of enhanced outbound velocities. Just a quick refresher, inbound velocities, which indicate particles moving toward the radar, are represented by greens, blues, and pinks, while outbound velocities indicate particles moving away from the radar and are represented by reds, oranges, and browns. When analyzing shear signatures, it's critical to know where the radar is located with respect to the couplet itself. In all of the upcoming examples, let's assume that the radar is located at the bottom of your screen, i.e. due south of the feature of interest. Horizontal shear can take on the form of convergence and divergence. Convergence occurs when winds come together. In radar velocity data, that would look something like this, with the area of inbounds on the far side relative to the radar and the area of outbounds on the near side. You can see how this represents convergence. The winds within the couplet are blowing toward each other. On the other hand, divergence happens when winds spread apart. Therefore, a divergent signature is just the opposite of a convergent signature, with the area of outbounds on the far side relative to the radar and the area of inbounds on the near side. The winds are blowing apart or diverging. If you were to draw an axis directly through the middle of a convergence or divergence couplet, it would be oriented parallel to the radar beam. An example of a phenomenon that produces a divergent signature in velocity data is a downburst.
Getting home alive is the goal. That's why these rules matter. Free ebook link in description.
Now let's add rotation into the mix. Cyclonic rotation occurs when winds spin counterclockwise around a center. In radar velocity data, that would look like this. If you were looking at the cyclonic couplet from the radar site, the area of enhanced inbounds will be to the left of the area of enhanced outbounds. In contrast, anticyclonic rotation occurs when winds spin in a clockwise direction around a center, which on radar looks like this. The area of enhanced inbounds is always to the right of the area of enhanced outbounds when viewed from the radar site. This time, if you were to draw an axis through the middle of a cyclonic or anticyclonic couplet, it would run perpendicular to the radar beam. Mesocyclones and tornadoes combine aspects of both convergence and rotation, which is typically cyclonic, so the axis of a couplet associated with a mesocyclone or tornado may not always be purely perpendicular to the radar beam. That brings us to a special kind of couplet called a tornado vortex signature, or TVS. As its name suggests, a TVS is a concentrated area of intense rotation evident in velocity data that suggests the presence of a tornado. Given the variety of different sizes, shapes, and intensities that tornadic vortices can exhibit, there are few official thresholds defining exactly what constitutes a TVS. In a very general sense, the smaller and/or more intense a couplet is, the more likely it represents a tornado, but it depends on the environment and the couplet's distance from the radar, among other factors. The intensity of a TVS is calculated by finding a variable called delta V, which is the difference between the maximum outbound pixel and the maximum inbound pixel within the vortex signature. Delta V does not correlate directly to tornado intensity. Instead, rotational velocity, or VROT, is a much better estimator of tornado intensity from radar data. VROT is simply half of delta V. In this example, I found, using this program's inspector tool, that the maximum outbound velocity within this TVS is 97.3 miles per hour, and the maximum inbound velocity is negative 52.6 miles per hour. Plugging these values into our equation, we get a delta V value of 149.9 miles per hour. Dividing this by 2, we get a VROT value of about 75 miles per hour. National Weather Service radar algorithms identify a TVS as a rotational couplet that has a delta V greater than or equal to 90 knots, or about 100 miles per hour, at a range of less than 35 miles from the radar site, or greater than or equal to 70 knots, or about 80 miles per hour, at a range of between 35 and 65 miles from the radar site. Because the radar beam increases with height above Earth's surface the farther out it travels from the radar, tornadoes and supercells that are even more distant from the radar may evade detection, and any rotational signature that does appear might only be attributed to the parent mesocyclone, given how high up into the storm the radar would be sampling at its lowest elevation angle. Describing a vortex signature by both its intensity and size is preferred. For example, if a rotational signature close to the radar meets the TVS criterion of a 100 mile per hour delta V, but the distance between the maximum inbound and maximum outbound pixels is several miles, you may only be observing a mesocyclone rather than a tornado. Generally, when the distance between the maximum inbound and maximum outbound pixels of a couplet is less than or equal to about 2 kilometers, about 1.25 miles, you are dealing with a TVS. This should not be considered a hard and fast threshold, as there are many exceptions, but it's at least a general rule of thumb to utilize when out in the field. Sometimes TVSs can be a bit tricky to identify, but there are some things that can help you ascertain whether or not a rotational signature is legitimate. As previously mentioned, knowing where the radar is located relative to the couplet in question is key. If you see a couplet but are unsure whether or not it's rotational in nature, identifying where the radar site is will lend clarity to which direction the winds are blowing within the couplet. For example, at first glance, this might look like a legitimate rotational signature. However, given that the radar is located just northwest of the couplet, we can clearly tell that this is a divergent signature. Also, TVSs are always symmetric across a radial, whereas convergence and divergent signatures run along radials. If an apparent rotational signature looks like a TVS but is not split in half by a radial, with most or all of the outbounds on one side and most or all of the inbounds on the other, it is not a true TVS. TVSs are generally persistent features as well. In the vast majority of cases, they last longer than one radar scan and therefore can be tracked over time. If a possible rotational signature appears in one scan and completely goes away in the next, that rotational signature is likely bogus. Similarly, they should possess vertical continuity as well. As you go up an elevation angle, there should be a TVS or at least some manifestation of a robust mesocyclone. Don't be alarmed if the vortex signatures aloft are displaced from the low-level vortex signature. This signifies the tilt in the supercell's updraft and, in turn, the entire vortex, induced by deep layer vertical wind shear. The exception is for non-supercell or landspout tornadoes, which are not associated with a parent mesocyclone. Landspout tornadoes begin at the ground and are quite shallow, so they may only be sampled by a radar at its lowest elevation angle. A TVS's location within a storm should also make sense. In a supercell, it should be located at the tip of the hook echo, or if a hook echo doesn't exist, near the rear flank of the storm. In the northern hemisphere, this tends to be on the supercell's south or southwest side. Sometimes, in lieu of a hook echo, you may see a bounded weak echo region, similar to what we discussed in episode 2, colloquially called a donut hole. As we discussed in the previous episode, tornadoes tend to occur at the interface between the forward flank and rear flank downdraft gust fronts. Often, you can make out the rear flank downdraft gust front in reflectivity data as a fine line draped downward from the tip of the hook echo, as well as in velocity data as a subtle convergence boundary wrapping into the TVS. Sometimes, anticyclonic tornadoes can develop near ongoing tornadoes, often along the rear flank downdraft gust front. On occasion, couplets will appear in the forward flank precipitation core, or even in the precipitation-free inflow notch of a supercell displaced from the hook. These are illegitimate TVSs and are the result of radar artifacts, which we'll discuss in a future episode of this module. In a squall line, TVSs are often coincident with small kinks in reflectivity along the leading edge of the line, or in supercells embedded within the line. TVSs in squall lines can often be difficult to detect, as they often appear small, asymmetric, and fairly weak, and they tend to be quite transient in nature. Sometimes an area of cyclonic rotation can develop at the northern end of a bow echo, which is called a bookend vortex. Bookend vortices can produce significant damaging winds and tornadoes. Standard base velocity measures the target's velocity with respect to Earth's surface, which is stationary. However, storms and storm-scale phenomena, like tornadoes, almost always move with respect to Earth's surface. Base velocity estimates the portion of a target's velocity that's moving directly toward or away from the radar, i.e. along a radial. This also includes the motion of the parent storm, which can make it difficult to obtain proper velocity measurements. For example, if a target within a storm has a velocity of 40 miles per hour, in essence the storm has 40 mile per hour winds, and the storm is moving directly at the radar at 30 miles per hour, the base velocity product will estimate the target's velocity to be 70 miles per hour, which is erroneous. This can mask rotational signatures like TVSs, making them difficult to analyze properly. To combat this, we can use a product called storm relative velocity. This is just like the base velocity product, only with storm motion subtracted out. So, in our example of a target moving at 40 miles per hour within a storm moving directly at the radar at 30 miles per hour, the storm relative velocity product would estimate that target's velocity to be a more accurate 40 miles per hour because storm motion has been subtracted out. Storm relative velocity is especially effective in identifying TVSs in QLCSs, as well as in situations in which supercells are moving very quickly. Let's take a look at an example. On the left is base reflectivity, and on the right is base velocity. Here we have a supercell thunderstorm moving at 55 miles per hour away from the radar site, which is located just off the bottom left corner of the image. As you can see, the supercell possesses a well-defined hook echo, as denoted by the yellow arrow. At the tip of the hook, we see an area of strong outbound winds, but very little in the way of inbound winds. At first glance, you might overlook this signature given its asymmetric nature, but when we switch to storm relative velocity, we see a much clearer depiction of a TVS, with an area of strong inbounds adjacent to an area of strong outbounds. This makes sense. Let's say our inbound winds within this TVS have a velocity of 55 miles per hour moving toward the radar. With a storm motion of 55 miles per hour away from the radar, the resultant base velocity reading would be an erroneous 0 miles per hour, and our outbound velocities would be drastically overestimated. With storm motion factored out, we get a much more realistic depiction of the velocities within the couplet and a much clearer indication of a TVS. At the time of this radar image, an EF3 tornado was ongoing, which highlights the importance of using storm relative velocity rather than base velocity in tornadic situations. In addition, TVSs within QLCSs can sometimes be difficult to ascertain given their typically weak and brief nature. While this can be the case regardless of the velocity product used to analyze them, storm relative velocity can help in this regard. Base velocity is more effective in identifying straight-line wind gusts, including downbursts, particularly at the lowest elevation angle. One issue that can plague intense TVSs is called velocity aliasing. Recall from the first episode of this module that every radar has a maximum unambiguous velocity, or Vmax. If a target is moving so fast that it exceeds the amount of phase shift the radar can detect, its velocity will become ambiguous, meaning that the radar might think that it's stationary or moving the opposite direction at a much different velocity than what it actually is. Because it applies to both inbounds and outbounds, the maximum unambiguous velocity, which is also called the Nyquist velocity, dictates the range of velocities that can be observed without this ambiguity. In other words, velocities that fall between positive and negative Vmax will be estimated accurately in velocity data. This range is called the Nyquist interval. Sometimes, winds within a TVS can be so intense that they exceed the Nyquist velocity, which causes them to exhibit much different velocities on radar than they actually have. For example, let's say a radar with a Nyquist velocity of plus or minus 70 miles per hour is sampling a TVS. Let's say a target within the TVS has an actual outbound velocity of 100 miles per hour. The radar will attempt to estimate the target's velocity, but it maxes out at 70 miles per hour. To compensate for this, the velocity folds over to the other end of the Nyquist interval and continues along the interval to account for the remainder of the velocity. In this case, the Nyquist velocity is 30 miles per hour shy of the target's actual 100 mile per hour velocity, so we'd go an additional 30 miles per hour, which gives us a radar estimated velocity of negative 40 miles per hour. So, the radar thinks that our target, which is actually traveling at 100 miles per hour away from the radar, is instead traveling at 40 miles per hour toward the radar. Let's say our outbound target was traveling at 150 miles per hour. The radar would read it as 70 miles per hour plus another 70 miles per hour plus the remaining 10 miles per hour, giving us an output of 10 miles per hour away from the radar, much different than the target's actual velocity. This can make TVSs and other signatures of intense winds difficult to properly analyze. Instead of a symmetric signature between adjacent enhanced inbounds and outbounds, you might see inbounds where there should be outbounds and vice versa, as in this example. Thankfully, all National Weather Service radars use an algorithm to de-alias velocity data, so most of the time we don't have to worry about velocity aliasing. Still, the algorithm can leave behind some aliased velocities at times, so it's good to know what to look out for. Another product that can come in handy when trying to identify a TVS is spectrum width. In reality, a single radar pixel can contain millions of targets, each with its own velocity. The radar averages the velocities of all the targets within a single pixel to come up with the velocity value for that pixel. Spectrum width is the range of velocities within a single radar pixel. In situations of high atmospheric turbulence, such as within a tornado, targets tend to move in a varied, chaotic fashion. The range of velocities in a given pixel is large, and therefore spectrum width will be enhanced at the location of the TVS. The various targets within the vortex, both meteorological and non-meteorological, have different aerodynamic qualities, yielding a wide range of velocities and high spectrum width. Spectrum width also does well identifying boundaries, especially when they may be shrouded by precipitation in reflectivity data. Prior to the advent of dual polarization radar, meteorologists were unable to confirm whether or not a tornado was in progress solely from radar data. However, because dual polarization radar can analyze the horizontal and vertical characteristics of targets, we can now tell whether or not debris is being lofted by an ongoing tornado. This is manifested in a feature called a tornado debris signature, or TDS. TDSs appear in correlation coefficient data as a small area of lowered correlation coefficient co-located with a tornado vortex signature. Correlation coefficient tells us how similar or correlated the targets are that a radar samples. In a tornado, each piece of lofted debris has different horizontal and vertical characteristics, as well as different orientations. This dissimilarity yields a decrease in correlation coefficient within the tornado. Tornadoes can loft debris quite high into the atmosphere, so a TDS at the lowest elevation angle may also be accompanied by a debris signature at higher altitudes as well. In fact, if a tornado vortex signature is within 80 miles of a radar site, tornado intensity can be estimated using a combination of rotational velocity and the maximum height of the TDS. As illustrated in this chart, in supercells, weak tornadoes, EF0 to EF1, tend to feature a rotational velocity at or below 40 knots or 46 miles per hour and a maximum TDS height under 8,000 feet above radar level, while violent tornadoes, EF4+, typically have VROTs in excess of 85 knots or 98 miles per hour and maximum TDS heights of over 18,000 feet above radar level. Some of the most intense tornadoes can loft debris over 20, 30, even 40,000 feet above ground. In addition, the rotational velocity thresholds are slightly lower for QLCS tornadoes, and there can be some overlap in VROT and maximum TDS height between weak and strong and violent tornadoes. Again, a TDS must be located in the same spot as a tornado vortex signature, otherwise it's a false alarm. In this example, notice that this area of lowered correlation coefficient does not correspond to a TVS. As a result, this TDS is illegitimate. TDSs are also persistent features. They will not just show up for one scan and then completely disappear in the next. Lofted debris takes time to fall out of the sky, so even after a tornado has dissipated, a debris signature is often present in correlation coefficient data, albeit less concentrated and intense. On the other hand, not all tornadoes produce a TDS. Some tornadoes may not be strong enough to loft debris to the height of the radar beam, or they may traverse areas with very little debris to loft. In these situations, you may not be able to confirm that a tornado is in progress just from radar data, but when a legitimate TDS is present, a tornado is definitely occurring. While correlation coefficient provides the most effective way to see lofted debris via radar, differential reflectivity also has utility in this regard. The random orientation and irregular shape of tornado debris typically yields an area of low differential reflectivity coincident with the tornado vortex signature. In addition, intense, damaging tornadoes can exhibit a reflectivity feature called a debris ball. This is a small area of enhanced reflectivity coincident with the TVS at the tip of a supercell's hook echo. The large size and concentration of lofted debris in and around a tornado returns an increased amount of energy to the radar, which yields enhanced reflectivity. On rare occasion, very little precipitation may wrap around a supercell's mesocyclone, creating what's called a low reflectivity hook echo. In this case, the first sign of a tornado may be a debris ball that appears to be detached from the parent supercell. So, the underlying message is that if you're unsure whether or not a rotational signature is legitimate, use multiple radar products to confirm as well as the rules of thumb we discussed. Let's take a look at a couple examples. Let's say you're out chasing and you're approaching this storm. We can clearly see that it's a supercell. It has the classic V-notch or flying eagle. It has a robust reflectivity core with very tight reflectivity gradients along its outer edges, and it has a clear kidney bean shape with a little bit of an appendage on its west or southwest flank. Then you notice this rotational signature, but you're not sure if it's legitimate. Let's go through our checklist. The first question you can ask is it in the right part of the storm? If the answer is no, you can usually disregard the signature altogether. In this case, the answer is yes. It's clearly coincident with the supercell's appendage. But let's go through our other rules of thumb to make sure. Is it symmetric across a radial? Yes, it's clearly split in half along a radial, with our enhanced inbounds on one side and enhanced outbounds on the other. Has it been persistent? If we go back a few minutes, we can see that there's been some sort of rotation in that area of the storm for multiple scans now, so yes, it has been persistent. Does it have vertical continuity? If we go up in tilts, we do see some sort of rotational signature all the way up to tilt 4. So we've been able to check all of our boxes. Where's our radar? Down to the south of the storm, so this is definitely a legitimate cyclonic rotational signature, and with a maximum inbound velocity of negative 32.4 miles per hour and a maximum outbound velocity of 76.1 miles per hour, that gives us a delta V of over 108 miles per hour at a distance of about 60 miles from the radar, which satisfies the criterion for a tornado vortex signature. Can we confirm a tornado with this TVS? Taking a look at correlation coefficient, we don't see a concentrated area of lowered values coincident with the TVS. Although we do have lowered values here, they're part of this broader area of lowered CC, rather than a concentrated area of significantly lowered CC compared to areas around it. You could also look at differential reflectivity and spectrum width, but unfortunately this particular archive is missing those products. So there's not enough evidence to confirm a tornado debris signature and therefore a tornado with this couplet, but it's clearly a legitimate tornado vortex signature. How about another one? Here, again, we have a supercell with an apparent cyclonic rotational signature. Right away, however, we can see that it's not in the right part of the storm. Instead of being co-located with the supercell's appendage, it's situated on the edge of the forward flank. This should immediately tell you that this signature is bogus, but to make sure, let's go through our checklist. Is it symmetric across a radial? Yes, it actually is. Has it been persistent? Going back a few scans, it seems to appear out of nowhere with little sign of any pre-existing rotation, so no, it has not been persistent. Does it have vertical continuity? No. As we go up in tilts, there's no evidence of any mesocyclone or vortex in the vertical. So, while at first glance it appears to be rotation, it fails a number of points on our checklist and therefore is not a valid vortex signature. Close visual observation of a supercell can provide clues that tornado genesis is about to occur, but there are a few radar signatures that can tip you off as well. The first of these is called a Differential Reflectivity Arc, or ZDR arc for short, which is an area of increased differential reflectivity that usually occurs on the right edge, which is typically the southern edge, of a supercell's forward flank downdraft along the reflectivity gradient. The ZDR arc occurs due to a preponderance of oblate, or flattened raindrops that become confined to this region, a process called size sorting. The mechanism behind this size sorting process is the veering and strengthening of the winds with height, i.e. vertical wind shear, that occurs in supercell environments, as smaller raindrops that fall with lesser velocity are advected farther from their source region than larger raindrops that fall more quickly. On the same token, the ZDR arc is tied to storm relative helicity, which is essentially a measure of the potential for cyclonic updraft rotation in supercells, generally below 3 kilometers above ground level. Storm relative helicity is an estimate of streamwise vorticity in the environment. Vertical wind shear creates horizontal, rotating tubes of air, which is a manifestation of horizontal vorticity or spin. When the wind feeding into a storm blows parallel to these tubes, the wind itself is spinning and the vorticity is considered streamwise. When the wind blows perpendicular to these tubes, the wind itself is not spinning and the vorticity is considered crosswise. Streamwise vorticity ingested by a storm induces updraft rotation from the get-go, whereas many storm-scale processes must occur before an updraft in a crosswise vorticity environment can attain rotation. Think of it as a quarterback throwing a football to a wide receiver. If the quarterback throws the ball with a perfect spiral, the wide receiver can easily catch the ball and run it into the end zone for a touchdown. This is akin to streamwise vorticity. In contrast, if the quarterback throws a wobbly ball, the wide receiver may have to bobble the ball a bit before bringing it in, making the catch more complicated. This is akin to crosswise vorticity. Streamwise vorticity is much more favorable for inducing supercell tornado genesis than crosswise vorticity. Therefore, because the ZDR arc is tied to environmental storm relative helicity and streamwise vorticity, a ZDR arc can be a sign that tornado genesis may soon occur. The development of a ZDR arc can signal that a storm is experiencing increasing storm relative helicity and potentially greater streamwise vorticity ingestion, both precursors to tornado production. In addition, the separation between the ZDR arc and a feature called a KDP foot can indicate that tornado genesis is imminent. A KDP foot is an area of enhanced specific differential phase that represents the heaviest precipitation within the supercell's core. Like the ZDR arc, the KDP foot arises from size sorting induced by vertical wind shear. Loeffler and Kumjian 2018 came up with a separation vector drawn from the centroid of the KDP foot to the centroid of the ZDR arc. They determined that the separation vector's magnitude, i.e. the distance between the centroid of the ZDR arc and the centroid of the KDP foot, tends to maximize around the time of tornado genesis. They also found that the separation vector tends to become more perpendicular to storm motion leading up to tornado genesis, and that both storm relative helicity and streamwise vorticity tend to increase with increasing perpendicularity between the separation vector and storm motion. When the separation vector and the storm motion vector are more parallel to each other, the vorticity is more crosswise. In this example, reflectivity is on the top left, storm relative velocity is on the top right, differential reflectivity is on the bottom left, and specific differential phase is on the bottom right. The ZDR arc and its centroid, along with the KDP foot and its centroid, are denoted as in the previous graphic. The separation vector, abbreviated SV, and storm motion vector, abbreviated SM, are displayed off to the side of the supercell in the reflectivity panel with red and blue arrows respectively. The time relative to tornado genesis is given in the top right corner. Notice how the separation vector and storm motion vector become more perpendicular with time leading up to tornado genesis. In fact, in the scan just 3 minutes before tornado genesis, the two vectors are nearly perfectly perpendicular to each other, indicating a shift to almost purely streamwise vorticity ingested by the supercell, and the tornado begins shortly thereafter. Mini supercells, especially those in more tropical environments, including those near tropical cyclones or their remnants, tend to display a mesocyclonic velocity enhancement signature, or VES, which is a small region of enhanced velocities greater than about 35 miles per hour between 7 and 14,000 feet above ground level on the right flank of a mesocyclone. VESs occur when mini supercells deviate from the mean flow, which yields an asymmetric velocity pattern within the mesocyclone, and they tend to be located above the low-level inflow region and co-located with the low-level mesocyclone and hook echo. Velocity values within the VES tend to maximize 1 to 4 volume scans prior to tornado genesis. Just like tornado genesis, certain radar signatures can provide clues that tornado dissipation is about to take place. Many of you may be familiar with the occlusion process of a cyclic tornadic supercell. This occurs as the rear flank downdraft wraps completely around the low-level mesocyclone, cutting it off from the warm, moist inflow needed to sustain tornado production. As this occurs, you'll often see the TVS begin to turn to the left of its previous track on radar, sometimes even making a full loop before dissipating. A new low-level mesocyclone often develops close to where the old one was, leading to renewed tornado genesis. Always be aware of the potential for leftward deviation near the end of a tornado's life cycle, as this can happen without warning and can lead to a perilous situation if you're located north of a tornado. In addition, several polarimetric signatures can develop in the lead-up to tornado dissipation. As described in Siegel et al. 2022, a decrease in intensity or disruption of the ZDR arc can be a sign that negative buoyancy is impacting the near-surface environment beneath the mesocyclone, which is unfavorable for tornado maintenance. This can also be a harbinger of decreasing near-supercell storm relative helicity. A decreasing angle between storm motion and the separation vector we just discussed can also indicate that tornado dissipation is imminent. Finally, precipitation within the hook echo tends to increase in intensity before tornado dissipation, which is often illustrated by an increase in KDP. These products are derived from our foundational base products, reflectivity and velocity, using known meteorological relationships. Before we get started, we must go over one important caveat when using these derived products and algorithms. Some of you may be aware of composite parameters in severe weather forecasting, such as the significant tornado parameter, or STP. STP attempts to boil down the incredibly complex set of ingredients needed for significant tornadoes into one number. While it can be a quick and easy way to get a broad overview of significant tornado potential, it completely ignores many of the intricacies that may arise in a given environment, and therefore should not be used as the crux of a forecast or storm chasing decision. The same holds true for derived radar products and algorithms which are not directly measured by the radar, and instead are mathematical manipulations of the base radar products. Every derived product and algorithm has inherent issues in how its output is calculated and uncertainties in the end product. Therefore, they should not be used on their own to make nowcasting decisions. Instead, they should be used as a tool within a broader toolbox of radar products to effectively analyze severe storms. Let's dive into the main derived products and algorithms you might use when out in the field. Let's start off with perhaps the simplest derived product, which is composite reflectivity. Composite reflectivity displays the highest reflectivity value within every vertical column of bins or pixels, regardless at which elevation angle it occurs. It can work well when monitoring for storm initiation, as precipitation droplets or ice crystals can initially develop at a much higher elevation angle than the lowest tilt. In this case, the composite reflectivity product may show robust returns well before the base reflectivity product shows anything at all. In addition, composite reflectivity is useful in situations in which the radar beam is blocked by terrain features or other objects, a problem in places like Southern California, Southern Arizona, and New Mexico, among others. Really any radar site that's perched near or in the mountains. The radar beam at the lowest elevation angle, or even multiple elevation angles, can be blocked by mountains, leading to a lack of echoes even when storms are ongoing. The composite reflectivity product can combat this because it displays the highest reflectivity value within every vertical column, which neglects the elevation angles that are plagued by beam blockage. For example, a strong thunderstorm was ongoing north of Roswell, New Mexico at the time of this base reflectivity image from the KHDX radar, but you might not know it. The KHDX radar is completely blocked in the low levels to the east by the Sierra Blanca Mountains, rendering the lowest two elevation angles useless. When we switch to composite reflectivity, we can much more clearly see the robust precipitation associated with the storm in question. Composite reflectivity does have its drawbacks, however. If the radar you're using does not suffer from beam blockage issues, composite reflectivity should not be used in lieu of base reflectivity, as many important storm features, such as hook echoes and boundaries, are easily masked by stronger reflectivity values at higher elevations. For instance, on the left is a base reflectivity image of a tornadic supercell with a very well-defined hook echo. On the right is the same supercell displayed using composite reflectivity, and as you can see, the storm just looks like an amorphous blob of precipitation with no evidence of a hook echo. Also, composite reflectivity tends to overestimate the quantity of precipitation that may be falling at the surface. The next derived product is called vertically integrated liquid, or VIL. The VIL product estimates the liquid water content in each vertical column of radar data by integrating the reflectivity values at all elevation angles in each column. Therefore, VIL is a good indicator of heavy precipitation in convective storms, with higher values representing heavier precipitation. VIL is a measure of mass per unit area, with units of kilograms per meter squared. Many chasers utilize VIL to determine whether or not a storm is producing hail, as well as how big that hail is. Because larger hailstones correspond to higher liquid water content, high VIL values can suggest that large hail is occurring. However, this practice is not entirely accurate, as VIL on its own is not a great tool to use to identify hail-producing storms. There are several reasons for this. One, VIL values depend on the characteristics of the air mass in which the thunderstorms are occurring. For example, storms in colder air masses may produce severe hail but still have low VIL values, while storms in warmer air masses may yield high VIL values but not produce severe hail. On the same token, because VIL is an integration of reflectivity through the depth of the storm, shorter storms tend to have lower VIL values than taller storms. This makes it difficult to distinguish between shorter storms with high reflectivity and potentially large hail, and taller storms with low reflectivity and no hail. Also, VIL values in storms that are quite close to the radar site are underestimated because the upper portion of the precipitation core may lie above the highest elevation angle of the radar. The same issue occurs in storms that are at the edge of the radar's domain, as the lower portion of the storm may be neglected. Finally, VIL can be significantly underestimated in storms whose updrafts are tilted, which happens in environments with strong vertical wind shear. VIL assumes that all the precipitation in a vertical column will fall downwards solely within that column. In environments with strong vertical wind shear, this is not the case. A storm's precipitation core would be tilted rather than mostly vertical, and therefore cannot adequately be sampled. Storms that move quickly enough to displace the upper portion of the storm significantly before a full volume scan can be completed may be associated with underestimated VIL as well. Because of all these issues, VIL must be used with dual polarization products to accurately assess large hail potential in a given storm. National Weather Service radars calculate two versions of VIL: traditional or legacy VIL and digital VIL, which is most commonly used today. Digital VIL was developed to deal with some of the aforementioned issues of traditional VIL. With traditional VIL, reflectivity values within each vertical column are truncated to 56 dBz to reduce the impacts of hail on the output, so any reflectivity values that exceed 56 dBz are reduced to that value. Digital VIL does not truncate reflectivity values, so it often yields a more realistic output. Also, digital VIL utilizes a more favorable coordinate system than traditional VIL. While digital VIL can provide more realistic outputs than traditional VIL, it still suffers from underestimation in situations with highly tilted updrafts and storms that are moving quickly. Thus, it still should only be used in tandem with other products to determine large hail potential within a storm. Our next derived product is the EchoTops product. The EchoTops product gives the maximum height of precipitation echoes detected by the radar that exceed 18 dBz between 5 and 70,000 feet above radar level. In essence, it estimates the height corresponding to the top of an area of precipitation, and it can be a decent proxy for how tall developing or ongoing thunderstorms are. The greater the EchoTops value is at a given point, the taller and stronger the updraft or storm is. Echo tops can help you monitor for convective initiation and can tell you which storms in a batch of storms are the most robust and may hold the greatest severe weather potential in the near term. A sister product to echo tops is enhanced echo tops, which helps smooth out irregularities that can sometimes appear in echo tops output and identifies areas where the radar could not compute a cloud top height. Its cleaner output makes it much preferred over the traditional echo tops product. Let's now move on to some algorithms you may find useful when chasing, the first of which is called the Hydrometeor Classification algorithm. This product uses a multitude of other radar products in an attempt to determine the predominant type of target, or hydrometeor, within the radar beam. The range of outputs runs the gamut from non-meteorological targets, such as birds or insects, to snow, rain, and hail, the latter two further separated by size or intensity. Hydrometeor classification can be a bit of a cheat code to identify precipitation type. However, you must remember that it determines the precipitation type at the height of the beam at a given location, which may not always be the same as what you might experience at the surface there. For example, it may identify hail at the height of the beam, but it may subsequently melt, reaching the surface as rain. A variation called the hybrid hydrometeor classification can also be used. It utilizes the relationship between reflectivity and precipitation rate to more effectively define the dominant hydrometeor within the radar beam. Both the hydrometeor classification and hybrid hydrometeor classification algorithms should be used in tandem with other radar products, namely the dual polarization products, to get the most accurate assessment of precipitation type in severe storms. Our next series of algorithms can help you identify important features and behaviors of storms. These are built into all National Weather Service radars, but not all radar software programs display them. The first of these is the Storm Cell Identification and Tracking Algorithm, or SCIT. SCIT identifies areas of precipitation that constitute actual storms whose basic attributes are calculated, such as maximum reflectivity value within the storm cell, probability of hail, and probability of severe hail, among others. Each storm cell is given a letter number identifier such as A1. In addition, SCIT can extrapolate what the storm's track might be for the following 60 minutes, including speed and direction. For new storm cells, this is estimated using the average motion of all cells in the radar domain or from environmental information. Keep in mind that the storm track does not apply to mesocyclones and tornadoes, but rather solely to the storm's precipitation core. If errors in the storm track are calculated, the storm track will be truncated from 60 minutes down to 45, 30, or 15 minutes, depending on the magnitude of the error. So if you come across a shortened storm track, know that uncertainty exists in that storm's track estimation. Also, SCIT tends to perform better when storm cells are isolated rather than embedded within a large complex of storms. Modern radars also feature the Mesocyclone Detection Algorithm, or MDA, which analyzes data for rotational patterns meeting specific criteria for size, strength, vertical depth, and duration. The MDA detects rotation on the order of 1 to 10 kilometers, which corresponds to a supercell's mesocyclone, and it calculates variables relating to the intensity and potential track of the mesocyclone. In most radar programs, mesocyclones detected by the MDA are identified with a circle. Color schemes for mesocyclone intensity may vary based on which radar program you use. Typically, green circles indicate weaker mesocyclones, while red and purple circles indicate stronger ones. Some radar programs differentiate between mid-level and low-level mesocyclones as well. For example, Gibson Ridge software uses a dashed circle for mid-level mesocyclones and a more solid circle for low-level mesocyclones. The Tornado Detection Algorithm, or TDA, is meant to detect tornado vortex signatures or rotation with a scale less than 1 kilometer. It works in much the same way as the MDA, but the TDA specifically looks for gate-to-gate shear, which is the shear between two adjacent pixels of velocity data, one inbound and one outbound, across a radial. To register with the TDA, the depth of the tornado vortex signature must be at least 1.5 kilometers, with its base at less than 600 meters above the surface, or at the radar's lowest elevation angle, or else it's deemed to be an elevated tornado vortex signature. Elevated tornado vortex signatures represent tight rotation aloft that can eventually develop into tornadoes. In most radar programs, a color-filled, downward-pointing triangle is used to represent tornado vortex signatures identified by the TDA. A hollow downward-pointing triangle is used for elevated tornado vortex signatures. Gibson Ridge software also provides a number within the triangle that represents tens of knots of radar-estimated delta V, So in this example, the 13 inside the triangle would mean a 130 knot delta V. The TDA does have some drawbacks. It requires a full volume scan to be completed, which can take as long as 5 to 6 minutes. This can significantly delay the detection of a tornado vortex signature. Also, it does not detect anticyclonic tornadoes. Finally, radars can analyze storms for hail using the Hail Detection algorithm, or HDA. The HDA calculates a number of probabilities and quantities by searching for reflectivities greater than 45 dBz above the freezing level, which is the level of the atmosphere where the temperature is 0 degrees Celsius. The higher these 45 plus dBz values exist above the freezing level, the greater the probability of hail, or POH. The probability of severe hail, or POSH, is related to how high these high reflectivity values are relative to the 0 degrees Celsius and negative 20 degrees Celsius levels, and tells us the likelihood of hail in excess of 3/4 of an inch. This is the old National Weather Service threshold for severe hail. Note that the current threshold is 1 inch. The maximum estimated hail size, or mesh, is also calculated. The standard symbol for hail identified via the HDA is an upward pointing triangle. Gibson Ridge software lists the hail size in inches within the triangle, and a larger triangle is used when a probability of severe hail exists. The HDA works best when a storm is between 35 and 70 miles from the radar site. Outside of this range, the HDA's efficacy decreases. All of these derived products and algorithms should be used with caution and in tandem with other radar products to get the clearest picture of what's occurring within storms. In particular, the mesocyclone, tornado, and hail detection algorithms often produce false alarms, so using them alongside the suite of base and dual polarization products will lead to a much more accurate analysis. Also, not every radar program will have these derived products and algorithms available to you. We're going to take a look at some errors and artifacts that can appear in radar data, including how you can identify them and how you can address them in your analysis. First, let's dive into some of the issues that can arise with data both near and distant to the radar. Radars have distinct limitations on how high they can scan in the vertical. The highest elevation angle that a National Weather Service radar can sample is 19.5 degrees. At just 5 miles from the radar, this corresponds to an altitude of about 11,000 feet, which is only about 20% or so of the depth of typical springtime supercells. Adding more elevation angles would significantly increase the time it takes for a radar to complete a volume scan, which would be extremely detrimental in severe weather scenarios. This brings us to the main problem with analyzing data close to a radar site, the cone of silence, which is a conically shaped region above the highest elevation angle that the radar simply cannot sample. On a two-dimensional radar image, the cone of silence will appear as a circular region free of data surrounding the radar site. This can impede the analysis of storms very near or on top of the radar site. There's not much you can do in these cases except to wait for the storm to fully move out of the cone of silence and use other radar sites if available, as well as other data sources such as satellite imagery to assess the storm.
The Chaser Academy is the best deal in storm chasing, and it costs less than a combo meal at McDonald's. Unlock instant access to exclusive storm chasing presentations, participate in live group coaching sessions, and get answers to all of your questions in the unlimited Q&A chat. Whether you're a beginner, a veteran, or somewhere in between, our expert coaches will help you take your storm chasing experience to the next level. Click the join button below this video or on our profile page and enroll in the Chaser Academy right now.
Another problem that can plague radar data within about 20 miles of a radar site is ground clutter. Because the radar beam is very near the surface within this range, part of it can interact with non-meteorological objects near the ground, such as buildings, wind turbines, highways, and more. Ground clutter often features high reflectivity and sometimes velocity values that can look like actual storms, sometimes with missing data pixels interspersed. But the key differentiator is that ground clutter does not move. It may sometimes suddenly appear and disappear in the same area, rather than propagate in a specific direction. In addition, because of its non-meteorological nature, ground clutter is often associated with significantly reduced correlation coefficient, and differential reflectivity is often near zero, but can be variable. The ground clutter returns you see here are associated with wind turbine farms near Dodge City, Kansas, and are a permanent fixture around the Dodge City radar site. The degree of ground clutter on radar can increase when a phenomenon called superrefraction occurs. The speed of the electromagnetic waves emitted by radars is dependent upon the density of the air through which the waves move. Pressure, temperature, and moisture, all factors in atmospheric density, generally decrease sharply with height. As a result, atmospheric density decreases sharply with height as well, allowing the top portion of the radar beam to move more quickly than the bottom portion. This causes the radar beam to refract or bend toward the Earth's surface the farther it extends from the radar. When the temperature increases with height within a layer of the atmosphere, in other words, when a temperature inversion is in place, or if the decrease in temperature with height is less than is typical, the beam is bent toward Earth's surface more than normal, which is superrefraction. If the beam's curvature matches or exceeds the curvature of the Earth, it's called ducting. An advantage of superrefraction and ducting is that the radar beam can travel much longer distances than normal, helping the radar sample more distant precipitation or storms. However, the beam spends more time closer to the ground and, at long distances, can even intersect the ground, which can increase the intensity of ground clutter echoes. Sometimes, ground clutter can degrade actual meteorological returns, which can muddy the analysis of storms near a radar site. To combat this, you can utilize the tilt or tilts just above the lowest one. This will omit ground clutter returns but still give you a look into the low levels of the storm. Still, the lowest tilt should be used to identify features like tornadic vortices and boundaries. Just like data close to the radar can have issues, so can data far from the radar, particularly at distances greater than 50 to 60 miles. This is because the radar beam spreads out the farther it extends from the radar. Think about shining a flashlight in a dark room. The light spreads out and becomes more diffuse the farther it gets from the flashlight itself. The same thing happens with the radar beam. For every 10 miles the beam travels, it spreads out approximately 1,000 feet, so at 120 miles from the radar, the beam is over 2 miles wide. This has significant implications on the resolution of the echoes returned to the radar. Many storm-scale features easily seen in data close to the radar, such as hook echoes and boundaries, are often muddled or even fully masked at long distances from the radar. In addition, because Earth's surface is curved, the radar beam gets farther and farther from the ground the more it extends outward from the radar, aside from instances of ducting. At a distance of 100 miles from a radar site, the beam is about 10,000 feet above the surface, and at a range of 200 miles, it's about 29,000 feet above the surface. Therefore, the beam overshoots the lower portions of storms at long distances from the radar, making the analysis of low-level features like mesocyclones, tornadoes, and boundaries nearly impossible. This is especially the case in radar holes, which are areas that feature little to no low-level coverage from any radar. This map shows the radar coverage at 4, 6, and 10,000 feet above ground level, indicated by the yellow, gold, and blue shading respectively. Areas in white receive no radar coverage below 10,000 feet. You can see that several areas that frequently experience severe weather lack robust low-level radar coverage, including parts of New Mexico, Texas, southeast Oklahoma, Nebraska, and the Dakotas. Unfortunately, these issues are without a viable solution aside from adding more radars. For example, let's look at the supercell that produced the Barnsdall, Oklahoma EF4 tornado on May 6, 2024, using two different radar sites. First, we'll look at the supercell from the Tulsa radar site KINX, located about 40 miles from the storm. Note the well-defined hook echo and rear flank downdraft gust front boundary, evident in both reflectivity and velocity data, as well as the strong tornado vortex signature. Now let's switch to the Oklahoma City radar KTLX, located about 90 miles from the storm. The aforementioned features are no longer evident, and the storm looks a lot more amorphous. This is a result of the beam spreading out significantly at this range compared to that of the Tulsa radar, degrading data resolution. Also, the velocity couplet is a bit broader as well. In this case, the beam was about 9,400 feet above the surface, so we're only getting a look at the mid-level mesocyclone and are unable to make any clear determinations about any tornadic activity from just the reflectivity and velocity data. Intense tornadoes can loft debris tens of thousands of feet into the atmosphere, so in these situations, correlation coefficient may still be helpful. Alright, let's now take a look at some specific artifacts and errors that can show up in radar data. Earlier we talked about ground clutter, which is one of many non-meteorological phenomena that can occur. Biological scatterers, namely insects, birds, and bats, can also appear on radar. The large region of slightly enhanced reflectivity that tends to envelop radar sites during some evenings is called bloom, and it's due in part to all of the insects that fly around at night. Birds and bats will often produce uniform rings or circular areas of slightly enhanced reflectivity emanating outward from a point. Most of the time, biological scatterers will produce reflectivity values less than 20 dBz, but occasionally they can exceed 30 or 40 dBz. Typically, they're associated with uniformly high differential reflectivity, but low correlation coefficient. During training exercises, military aircraft sometimes emit strips of aluminum called chaff, which is highly reflective and hides the aircraft from enemy radar. Chaff can be easily mistaken for precipitation, as it often takes on the shape of a storm on radar and moves just like a storm does as well. If an apparent storm or area of precipitation seems unusual given its location or background environment, be sure to check if there are any military bases in the area, and use correlation coefficient to confirm whether or not the echoes are legitimate. Chaff is associated with significantly decreased correlation coefficient akin to other non-meteorological targets. Smoke plumes from large fires can also appear on radar as areas of slightly enhanced reflectivity that spread downwind from a single stationary point. They also feature extremely low correlation coefficient. While most radars are situated in areas that provide a clear view to the sky in all directions, some suffer from beam blockage, which is when things like buildings, trees, hills, and mountains obscure part of or even the entire beam in certain directions. Beam blockage can wreak havoc on storm analysis because it can cause the intensity of echoes to be drastically reduced, or, even worse, it can hide part or all of a storm from the radar's view. In these situations, using an elevation angle higher than the lowest one can help alleviate the beam blockage issue, and in extreme cases in which several tilts are affected, the composite reflectivity product can help you see the storm more effectively. For example, the Tucson, Arizona radar site KEMX is located in the mountains near the city, causing significant beam blockage issues particularly to its south and southwest. Focusing on this area, notice how the base reflectivity data shows little in the way of robust convection, but if we switch to composite reflectivity, we see several intense thunderstorms occurring. The next artifact is one that we introduced in our discussion of pulse repetition frequency and a quantity called the maximum unambiguous range, which is the maximum range within which a transmitted radar pulse can be scattered and received before the next pulse is transmitted. If a radar emits a pulse before the backscattered energy from the previous pulse is received, the backscattered energy will make it back to the radar, but the radar is unable to accurately tell which pulse it came from and how far the target is from the radar. This is called range folding, and it can have a significant impact on the readability of radar data. Thankfully, National Weather Service radars are equipped with methods to combat range folding, namely alternating between two different electromagnetic waveforms that each have different PRFs for the lowest few elevation angles. This almost always alleviates range folding in reflectivity data. However, radial velocity measurement relies on a single PRF, so range folding issues often plague velocity data. Range-folded pixels will appear as purple in most radar programs, indicating that the data cannot be recovered for those pixels. On the same token, every radar assumes that any returned echo is from the most recent pulse it emitted. If the radar receives backscattered energy from the pulse previous to the most recent, it thinks the return is from the latest pulse and, therefore, plots it closer than where it really is. These are called second-trip echoes, which manifest themselves as elongated streaks of echoes emanating outward from the radar along radials, where no active weather is occurring. Precipitation particles scatter most of the electromagnetic energy from a radar beam in all directions, including back toward the radar. However, a fraction of that energy is absorbed by the particles themselves. This can cause the radar beam to become less intense the more particles it passes through as it extends outward from the dish, a phenomenon called attenuation. The amount of energy that's absorbed and, therefore, the amount of attenuation depends on the intensity of the precipitation and the wavelength of the pulse. If a radar beam passes through a light shower, the attenuation will likely be fairly minimal, but if it passes through, say, the heavy precipitation core of an intense supercell, the attenuation will be much greater, often erroneously decreasing the apparent intensity of more distant storms in line with the supercell's core. Also, shorter wavelength pulses are more susceptible to attenuation. This is why terminal Doppler weather radars and mobile radars are best suited for close-range weather observation. They use a shorter wavelength than National Weather Service radars and, in turn, suffer from greater attenuation issues. In this example from the TOKC terminal Doppler radar in Oklahoma City, located at the Pink Star, the beam was shooting through very heavy rain to the radar's immediate west. The storm farther to the west was of equal intensity to the band of heavy precipitation, but notice how reflectivity within the storm was significantly lower than that of the band. This is a product of attenuation as the beam traveled through the initial heavy rain band. Up to this point, we've described the radar beam as being focused within a single lobe of energy. However, this is not exactly the case, as radars have an imperfect radiation pattern. This creates weaker auxiliary lobes of energy that occur both in the horizontal and vertical, called side lobes, that can sometimes impact data quality, particularly in the velocity product. Most of the time, the radar data we see is dominated by returns within the main lobe, and these side lobes have little impact on the overall output. But sometimes returns within side lobes dominate the total signal, as in this example here, where the side lobe features a much greater preponderance of hydrometeors, including rain and large hail, than the main lobe. This induces an artifact called side lobe contamination. Again, most of the time, side lobe contamination is not an issue, but it can be a major problem in regions with sharp changes in reflectivity, either horizontally or vertically. As it relates to storm chasing, a textbook example of this is in the inflow region of a supercell, which often features a strong vertical reflectivity gradient. Side lobe contamination manifests itself in velocity data as an erroneous area of rotation that can mimic a strong mesocyclone or tornado vortex signature, but is displaced from where rotation should be located within the storm. In other words, a side lobe contamination-induced couplet will not be co-located with a supercell's hook echo or rear flank. Side lobes are also the reason why ground clutter occurs, as they interact with objects at the ground rather than the main lobe. Let's take a look at an example. At first glance, it appears that a tornado may actually be in progress. We have a bona fide supercell, complete with well-defined hook echo and a strong, tight velocity couplet. However, upon closer inspection, notice how the velocity couplet is located in the inflow region of the storm, much closer to the edge of the forward flank. This is a classic sign of side lobe contamination. If this was a tornadic couplet, it would be located back in here, coincident with the tip of the hook echo. Also, note the lack of reflectivity in the vicinity of the couplet, but as we go up to the next tilt, we see strong reflectivity in this area, indicative of a strong vertical reflectivity gradient. This is evidence that the side lobes of the beam at the lowest elevation angle were encountering a much greater concentration of hydrometeors than the main lobe. Here's another example. Once again, we have a classic supercell with a well-defined appendage and a very strong velocity couplet. However, the couplet is located in the clear air well out ahead of the appendage, so this is side lobe contamination. In some cases, side lobe contamination can occur in tandem with legitimate rotation. In this example, we see two potential areas of rotation. The one on the left is co-located with the supercell's appendage, evidence that it's a legitimate rotational couplet, while the one on the right is side lobe contamination, situated in the storm's inflow region just south of the forward flank. You can see how easy it is to be fooled by one of these erroneous couplets, so always make sure that the velocity couplet in question is real when you're analyzing radar data. This graphic from Boettcher and Bentley 2022 gives a good workflow for diagnosing whether or not a circulation is legitimate or associated with side lobe contamination. Couplets induced by side lobe contamination will be misplaced from the hook echo or rear flank of the storm, typically with weak to no reflectivity in and around the false circulation. Although imposter couplets can mimic a tornado vortex signature fairly well, they also frequently take on a blocky, disorganized appearance that lacks a clear velocity gradient. Finally, there will be a tilt or tilts of enhanced reflectivity above the imposter couplet, which is evidence of ample hydrometeors for side lobes to sample. The final artifact we're going to discuss is called a three-body scatter spike, which is a telltale sign of large hail. When the radar beam encounters large hail within a storm, part of the energy within the beam can get deflected down to the ground, back up into the storm, and then back to the radar. It gets deflected 3 times, hence the name three-body scatter spike. This portion of energy arrives back at the radar slightly later than the original backscattered energy, so the radar assumes that it exists farther along the radial than the storm itself. The result is a spike of low reflectivity that extends along the radial outward from the storm's core. Three-body scatter spikes are also often accompanied by significantly decreased correlation coefficient. On rare occasion, damaging tornadoes can produce a three-body scatter spike as the radar beam deflects off of heavy lofted debris. In these cases, the three-body scatter spike will emanate from the debris ball at the tip of the hook echo in reflectivity. We're going to dive into storm interactions, which can play a major role in the types of hazards you can expect from supercells and can give you a clue as to which storm you should target or reposition for during an active storm chase. Much of this will be based on new research on storm interactions by Cameron Nixon and others. If you'd like to do some digging on your own, head over to the articles you see on your screen here. In environments with strong deep layer wind shear and or relatively dry air aloft, storm interactions are critical in allowing nascent updrafts to survive early on in their life cycle. Strong deep layer wind shear can be detrimental to purely isolated updrafts, causing them to fizzle out before they can become robust. On the same token, isolated young updrafts that ingest drier air aloft, a process called dry air entrainment, can experience less instability than what may be measured in the environment, allowing them to become pinched off and struggle to reach maturity. However, updrafts can overcome these issues by clustering together initially. The interactions that take place during this clustering phase can yield wider, more sturdy updrafts that withstand strong vertical wind shear and dry air aloft. Often, this progression results in one or two dominant supercells after the initial interactions are complete, so even though early clustering may give the appearance of a more messy storm mode, remain patient and wait for the interactions to work themselves out. For example, let's take a look at the convective evolution in southern Mississippi during the April 12, 2020 tornado outbreak. 60 to 70 knots of 0 to 6 kilometer shear was in place, which is quite strong. Notice how the initial evolution of the convection coming out of Louisiana was extremely messy. This was the result of numerous updrafts clustering together. However, this aided in storm intensification in the face of strong vertical wind shear. Eventually, two discrete supercells emerged after the initial interactions were complete, both of which became significant tornado producers. Had the initial updrafts been more isolated in nature, they likely would have struggled, and the outcome may have been quite different. Storm interactions remain crucial in convective evolution after storms mature into supercells. In order to produce tornadoes, a supercell needs to achieve a balance of inflow and outflow. Too much inflow and the residence time of vortices underneath the storm's updraft decreases. Too much outflow and the mesocyclone gets persistently undercut by cold air. Both of these scenarios are detrimental to tornado genesis. The amount of inflow that supercells in a given environment may have can be determined using a proximity hodograph. For those who aren't familiar, a hodograph is a plot of the wind speed and direction at each level of the atmosphere. We can draw a vector from our estimated storm motion, given by this black bullseye here, to the lowest point on our hodograph, which represents the surface. This vector illustrates our storm relative inflow. The longer that vector is, the more storm relative inflow supercells may have, and the more outflow that'll be needed to balance out the inflow. In this example, storm relative inflow was near 50 knots, which is very strong, so a lot of outflow would be needed to achieve the balance. In contrast, this environment features a very small storm relative inflow vector with a magnitude of about 20 knots, meaning that only limited outflow is necessary to achieve the balance. Now the question is, where does this outflow come from? Auxiliary storms near the rear flank of the supercell. As shown in their plots of the density of convection in proximity to a hypothetical supercell, Nixon et al. 2024 found that in cases of significant tornadoes, the amount of auxiliary convection near the rear flank of the storm tends to increase in the time leading up to tornado genesis. In contrast, for non-tornadic cases, secondary maxima in convection tend to be situated near the left and forward flanks of the supercell. In these scenarios, outflow from left and forward flank auxiliary convection tends to undercut the main supercell, throwing off the inflow-outflow balance in favor of outflow, which is unfavorable for tornado production. This dispels the common practice in storm chasing of targeting the most isolated supercell at the tail end of a band of supercells, colloquially called the tail end Charlie. In a pair of supercells, the lead supercell tends to be tornadic, while the trailing supercell generally produces mostly hail. The same holds true for a cluster of supercells. The lead storms are most likely to be tornadic, while the trailing storms are most likely to be mostly hail producers. Within a QLCS, supercells at the head or north end of the line are most apt to produce tornadoes, as are any embedded supercells within the line, while the tail end supercell tends to produce mostly hail. The stronger the storm relative inflow, the more rear flank auxiliary convection is needed to achieve the inflow-outflow balance. Often, the outflow from these auxiliary storms doesn't directly influence tornado genesis in the main supercell, but rather perturbations in the near-storm environment aloft induced by the auxiliary storms can be enough. On rare occasion, purely discrete supercells can produce tornadoes without any assistance from auxiliary storms, fueled only by the ingredients available within the ambient environment, but in the vast majority of cases, auxiliary storms are necessary. Let's take a look at some radar data of the multitude of storm interactions that can aid in tornado genesis in supercells. The first is the classic merger, in which an auxiliary storm merges into an established supercell. Storm chasers already monitor for these mergers closely, as they're known to frequently induce tornado genesis. They lead to the widening and strengthening of the main supercell's updraft and can increase outflow production to achieve the inflow-outflow balance. Mergers include a right-moving supercell colliding with another type of convective object, including a small shower or non-supercell storm, a left split from another supercell, or a QLCS. They can also include two or more right-moving supercells merging together to create one conglomerate supercell, as in this example here. In this case, the original supercell may hand off to the merging supercell, which then becomes dominant. The merging supercell takes on the conditions that the original storm was experiencing, leading to rapid intensification and, often, tornado genesis. The next type of interaction involves feeder cells. As their name suggests, these cells persistently feed into the rear flank of the supercell. Feeder cells can consist of only a couple trailing storms, or a whole line of storms, as in this example here. As we discussed earlier, the degree of storm relative inflow dictates the quantity of feeder cells that's necessary to achieve the inflow-outflow balance. Perhaps the most subtle of all storm interactions is the nudger. A nudger is a cell that moves into the vicinity of the main supercell's rear flank, sometimes not even fully interacting with it. In some cases, even a small shower can be enough to nudge a supercell toward tornado genesis, particularly in environments with weak storm relative inflow. Nudgers can also come in the form of a nearby supercell or a full-blown QLCS. Notice how the supercell undergoes significant tornado genesis as the QLCS approaches. On occasion, when two supercells interact, they can undergo the Fujiwara effect, which is when two vortices rotate around each other, often merging into one. This phenomenon is most prevalent in hurricanes, but the mesocyclones of two interacting supercells can sometimes orbit around each other, particularly when the storms are large and slow-moving. When this happens, the lead supercell tends to slow or move rearward toward the trailing storm while weakening, while the trailing storm accelerates or moves forward as it strengthens. Sometimes the two supercells can merge into one after the Fujiwara is complete, which can induce very large hail production or significant tornado genesis. Supercells undergoing a Fujiwara can pose great danger to storm chasers in close proximity to the storms, including erratic tornado motion, so always use extra caution when chasing two supercells in close proximity to one another.
Remember to check out those links in the description below, and then watch another video.